I apologize for the telephone call that I got at the end of the last lecture. I was trying to record and call came through even though I had put my phone on silent, but because it is linked to my computer, sometimes the it rings on my computer also. So this time I'm being smarter about that. I just switched off my phone while I'm doing the recording. So switching gears a little bit, uh, let's continue with talking about powder-based processes. So in this case, a combination of a powder-based process and laser energy types, laser or electron beam type of energies. So these are generically called powder bed fusion processes. So you are fusing these powders together. And this was among the first commercialized process at UT Austin, who started the students, Carl Deckard and his uh, advisor, they started a company called DTM Corporation, which was then later on taken over by 3D Systems. And now 3D Systems is manufacturing and selling these machines. So this was the first commercialized powder bed fusion process. So in this case, what we are doing is we have um, a bill platform and we have feed cartridges where the powder has been filled, and we have powder leveling rollers that will move this powder on top of this build platform. So every time you build one layer, this platform will go down by a small quantity, and then you have more powder being incorporated on top, and then you have a CO2 laser in this case, although CO2 lasers were found to be not the best kind of laser to be used for these applications. So people have started changing them. They are made, I mean, they are using what are called fiber lasers. So in this case, you have a CO2 laser that is controlled by a galvanometer, and that galvanometer will focus this laser beam on top and melt and fuse these powders together. So once the part is built, you just take it out, and there is nothing more to it after that. So they share a basic set of characteristics. So there is one or more thermal source for inducing the fusion between the powder particles, and then there is a method uh, for controlling the powder fusion to a prescribed region of each layer, and you have a mechanism for adding and smoothing the powder layers. So in this case, the selective laser sintering process was originally developed for making plastic prototypes, mainly from nylon. And they did a lot of work on extending it to metal and ceramic powders. And there were multiple variants on that. And what has happened is that now we have a broad range of materials, polymers, metals, ceramics, composites, everything. And now they call it direct digital manufacturing, or DDM, of end use products. And many companies are starting to use this process for making final components. For example, GE uses that for making parts for the um, which are turbine blades for their Gen X engines. Lockheed is making um, satellite parts. Northrop Grumman is making parts for the F-35 platform. And the good thing is that you get material properties that are comparable to many engineering grade polymers, metals, and ceramics. So you are going to get pretty good properties, so you can finally start making parts that are functional. So this is the this is a true functional prototyping process. So in this case, the selective laser sintering, when they started out, they said, they could make typically approximately zero point 0.1 millimeter thick layers, and they were spread across the build area using a counter rotating roller. Um, and the inside chamber could be controlled with nitrogen gas to minimize the oxidation and degradation of the powdered material. And the powders in the build platform is also maintained just below the melting point or glass transition temperature of the powdered material. So you have two different videos that I just input there. One is for the actual selective laser sintering. The other one is for making metal parts using this process, actual metal parts using this process. So one thing to note is that you have to heat the powders and keep them at an elevated temperature. And you also have to preheat the powder prior to spreading over the build area. And sometimes the build platform is also heated using resistive heaters. So the whole envelope is going to be heated. And this is required because using this approach, you can minimize the laser power requirements, and you also prevent or minimize the warping of the part during the build due to non-uniform thermal expansion and contraction. So that's very much required. So which means that again, it's going to be hot inside. So it's not unless you're working in an extremely cold environment. It's not extremely nice to be around this machine. But I mean, this is like a standard machine now. So a lot of changes have taken place since the time it was originally developed. So in this case, they used a CO2 laser beam, and the process will thermally fuse the material to form the slice cross section. And the important thing to note is that the surrounding powder remains loose and it serves as a support for the subsequent layers. So which means that you do not need a support structure just like the fuse deposition modeling or the selective laser sintering process. So you make that layer by layer and the process repeats itself until the complete part is built. And you have a cool down period because you can't just go and pick it out, because otherwise it's going to be exposed to the ambient temperature and atmosphere, or it might warp because of that sudden exposure to ambient temperature. And also the powders are going to be degraded. Now one thing to note is that these powders are going to be expensive. So if you expose them to atmospheric temperature and pressure, you are going to have degradation of the powders, so you can't recycle those powders very easily. So in order that you can recycle them, also you want to make sure that the part is going to be cooled down inside the build envelope itself. So in the powder bed fusion process itself, you have 4 different ways of fusing the powders together. The first one is called solid state sintering. Second one is chemically induced binding. The third one is called liquid phase sintering. And the fourth one, you're actually melting the whole thing and bonding the particles together. And it should be noted that most commercial processes utilize primarily liquid phase sintering and melting. So these are the four different powder fusion mechanisms in powder bed fusion. So you can have solid state sintering, chemically induced binding, liquid phase sintering, and full melting. In liquid phase sintering itself, you have two different possibilities. One is you have the binder and the structural materials are not separate from each other, which is used mainly for ceramic type of materials where you add a thermoplastic binder to it. Or you can have distinct binder and structural materials. You can have separate particles, you have composite particles, or you have coated particles. You can also have full melting in this case. So let's look at what is meant by solid state sintering. So you are fusing the particles together without completely melting at elevated temperatures. And it typically happens at approximately between about one half the melting point in degrees absolute and the melting temperature. That means when you do that, these particles are going to be uh, partially melted, and there is a necking that happens at the end of the particles, and they will just join them together. And you keep joining them together at, at each layer, and once that happens, you can make the whole part. The driving force is the minimization of the total free energy of the powder particles, and it is basically diffusion between the powder particles. Okay, um, I think this is a duplication of the previous slide. I'm sorry about that. So one thing to note is that the surface energy is proportional to the total particle surface area, and when you fuse the particles at elevated temperatures, you are going to be minimizing the total surface area, and so the total surface energy will decrease. So that is a driving force for this whole process. So this is a schematic of that. So you have unsintered particles together, and then once it starts getting fused, they will start fusing and they will start growing into bigger particles. So you start with a big hole in the middle, and then they will all start forming, and then they will decrease the porosity. So once the total surface area of the powder bed decreases, the rate of sintering will slow. So if you want low porosity levels, you have to increase the sintering temperature or have extremely long sintering times. Now that's probably not going to be very effective. So what they do is you do this at to a stage where you get reasonably low porosity. Then you do some post processing such that all the remaining porosity is completely removed. So you have processes such as uh, hard isostatic pressing, hard isostatic processing, or you may want to refill this with a metal, lower melting point metal that will fill all the holes and give you a completely dense part. Now, the surface area, the total surface area of the powder bed is a function of the particle size. So you will need lesser energy if your particle sizes are small, and you will have a greater free energy driving force if the surface area is high. So which means that smaller particles will sinter faster and initiate sintering at lower temperature than larger particles. When you are doing additive manufacturing, the, the cost for making a part is also based on the time it takes to make the part. So which means that the shorter the time it takes to form one layer, the less expensive it becomes to make the part itself. So which means that your fusing mechanism or the heat source should be able to move rapidly and induce fusion to increase the building rate. If you want sintering alone, as we saw earlier, that means it will take longer time. So most additive manufacturing processes will not use sintering as the primary fusion mechanism. So they will have to have something else, and fusion will only be a part of your, or sintering will only be a part of your mechanism. But it is still an important um, process, even though it is not the primary fusion mechanism. Okay. Now, when you do this, what happens is that because of the temperature effects, some of those particles are going to get agglomerated together. And so part of that bed will become much harder than the surrounding loose powder, so which will lead to part growth and change metallurgy. Scott will probably understand what I'm talking about. And if there is rapid fusion of the powders, that means some of those powders are not going to be good enough to join together. So which means that you are going to have distributed porosity through the entire part, which is not a good thing. So you have to have a balance between the two. So this is a typical microstructure of a nylon uh, microstructure, and you will see that there are multiple microstructures across the entire part, so which is not a good thing. So again, you have to have a good balance between the temperature you're using to bind the particles together, and you also have to have the right kind of properties that you end up with. So that's about it for the solid state sintering. Now we have the chemically induced sintering. So this is a variation of the solid state sintering process where you have a gas, or you have two different types of powders, and the powders and the gases will form a byproduct which will bind the particles together. And this is primarily utilized for ceramic materials. So for example, if you're laser processing silicon carbide in the presence of oxygen, you have silica, and it will form a composite between the silicon carbide and silica. Or you are processing zirconium diboride in the presence of oxygen, so you have zirconia that is formed. It will form a composite of zirconium diboride and zirconia. Now, and there are two more, but what you will find is that this may not be ideal for every single situation, because you may not want to have an oxide, especially if you are going to be in an oxidizing type of environment. You are going to be increasing the probability that this component is going to be oxidized. So if there is oxygen, so there is going to be um, unless it is going to act as a diffusion barrier, it is going to draw more oxygen inside, because there is going to be a variation in the oxygen content between the outside and the inside. So which means that this part is going to get oxidized extremely fast. So if you don't want that, this may not be the ideal process to make the part. The next one, which is probably the one process that is used in most uh, metal-based additive manufacturing processes nowadays. It is the most versatile process, and it is you are trying to fuse the particles together where one part of the particle will become molten while the other portions remain solid. And this process is also used in the cutting tool industry, and there is no need to melt or sinter all the particles together. So you are going to have some parts uh, partly fused and melted, and then they will all start bonding together and becoming one full solid. And whatever gaps you have, you take that and hard isostatically press it so that all the remaining porosity goes away. There is a clear distinction between the binding material and the structural material. So they can be combined in three different ways. One, you can have them as separate, or you can create them as a composite particle, or you can have a coated particle. So you have the low melting point material coated on top of the high melting point material. So this could also be used for ceramic particles, ceramic parts. So, but if it is a ceramic part, and if there is a binder that is binding the particles together, then what you have to do is you have to do what is called the debinding process to remove all the binder, and then you have to sinter the whole part together. The last process is full melting. So it is most commonly associated with engineering metal alloys and semi-crystalline polymers. So you are exposing the entire region of the material to heat energy to a depth exceeding the layer thickness, so that the top layer is going to be bonded well with the bottom layer, and it will remelt part of the bottom layer, and so that it will all join together. So you're going to have some amount of residual stresses, but it is a process that is used in many cases. And you can create a well bonded high density structure from engineering metals and polymers. So what materials are used for powder bed fusion? Nylon polyamide is one of the most common ones, especially for making prototypes. But nylon is also a good material for many different applications. For example, for making fuel tanks for unmanned aerial vehicles, UAVs. This is a standard process. Only thing is that when you make this part, there is going to be some powder left behind between the layers. So which means that all that excess material has to be removed completely before you start using them for storing fuel. Now, there are cases where you're going to be doing full melting. If you're going to be doing full melting, you are going to get part growth. And in some cases, if the powder bed is going to be hot around it, so you may not get good accuracy in the parts that you are going to be doing. So you have to have some amount of optimization in the parameters to have it between full melting and liquid phase sintering. Okay, so these are again, I mean, there are for metal-based powder bed fusion processes, there are many different alloys like engineering alloys, titanium, stainless steel, Ti64 are typically fully melted. And one thing to note is that when you make these parts, you're going to have some amount of non-isotropic nature. which is distinct from cast or wrought parts made from identical alloys. And if I recall correctly, I had presented you with some slides in the first set of slides for the first lecture for the microstructure. So please go look it up again. You will see the differences in the microstructure of an additively manufactured part versus a cast or wrought alloy. So when you make these parts, there are four requirements or characteristics required. One is you need to have a powder reservoir of sufficient volume to enable the process to build the maximum build height. So you shouldn't have to stop the process in between and go fill up the material. Now, is that going to be a problem? No, but you ideally want to avoid that if at all possible. And then once you are making it, it needs to have the correct volume of the powder being transported from the powder reservoir to the build platform. So you don't want to create excess layers and things like that, or the layer thickness should not be non-uniform from one part of the part to the other part. So which means that it has to provide the right amount of powder uh, when it is going from one layer to the other. And it should be spread to create a smooth, thin, repeatable layer of powder. So if you set it for say 500 microns, it should be 500 microns plus or minus so and so at every single layer. And the other thing to note is that when you are making these parts, because you're going to be melting part of the layer beneath, you do not want to create excessive shear forces that disturb the previously processed layers. There are certain precautions that you need to take, which are typically great challenges. When you decrease a particle size, you have faster sinterability, faster bonding, and things like that. But what does it do to the actual part itself, actual powder itself? So if the particle size decreases, they will tend to start clumping together, and which means that it will flow less. I mean, the flowability will be less. I don't know if flowability is a real word or not, but I hope you understand what I'm saying here. The most important issue with small particle sizes is that I don't know if you have ever seen a container of metal particles, metal powders, especially aluminum powders, titanium powders, and things like that. It is a fire hazard. It is an explosive material, and you got to be extremely careful in handling these materials. Second thing is that if you are going to be using them in your build process, they can become airborne and they can go and start depositing on top of the optics and things like that. So which means that over a period of time, your optics will start getting clouded. So which means the accuracy of your machine will go down. So sometimes you may want to change the whole optics, or sometimes you may want to go and clean the optics at regular intervals. Smaller particle sizes enable better surface finish, but they have all these problems. So you got to make sure that these problems are taken care of. How do you spread the powders? There are many different ways to do that. And the easiest one is by the counter leveling roller that you saw in the first set of slides for powder bed fusion process. So that is in the standard commercial selective laser sintering machine. The pushing force will fluidize a powder, Or you may put some powder and you have what is called a doctor blade, and it will come and smoothen the height, or make sure that the height is uniform. And if you have the doctor blade also vibrating, then you can partially fluidize the powders. Otherwise, it's not going to be fluidized at all. Or you may want to have a hopper feeding system where, especially if you're going to be making parts made from two different sets of powders, you could do that. You have two sets of hoppers coming and feeding the material. So if you want to make metal or ceramic parts, you can either do full melting or liquid phase sintering, or you may want to do indirect processing where you have a mix of a ceramic and a binder system. You put the particles together and then you debind it, and you sinter that, and any remaining porosity will be filled up with a low melting point alloy. Or the other thing to do would be to use these as investment casting patterns using a low melting point alloy. So there are many different variants of the powder bed fusion process. Um, you have laser based systems for low temperature processing. There are two major manufacturers, 3D Systems and EOS. And EOS has 3D Systems, and DTM before that had um, trademarked SLS, or selective laser sintering process. Um, but what used to happen was that you had a we would use CO2 lasers and a nitrogen atmosphere with some amount of oxygen in it. So you could not directly process pure metals or ceramics. And they were only good for processing things like nylon. But nowadays, um, these companies have started making them with fiber lasers and so on. So um, they are much better suited for high quality metal parts or high quality ceramic parts. So there are 4 European companies besides 3D Systems that are making commercially available systems. One is EOS in Germany, and their machine is capable of making Ti64 and chromium cobalt, which are mainly for bio-based applications and so on. You have a company called MTT Technologies in UK. They have no limitation in the type of powders that can be used, but which means that you are also at the mercy. So there are no safety precautions that the machine has, especially if you are going to be using very small powder sizes. Um, you have a company called Concept Laser, and their process, they came up with the terminology laser QCing. QCing is actually a combination of cladding and fusing. So you are cladding the material and you are fusing the particles together. And that process can be used for stainless steel, hot work steel alloys, aluminum alloys, and things like that. And so for making aluminum, this is one of the few machines that can make parts, 3D parts from aluminum. So in all these, then there is Phoenix system in France. They can do ceramic and high melting temperature metallic alloys. So in all these things, there is a terminology called selective laser melting. So this is the term used to describe the technology in a generic way. So what are the changes from previous machines? So CO2 laser has been changed to, first they changed to neodymium YAG, but then now we have fiber lasers which are cheaper to purchase and maintain. It is much more energy efficient and have better beam quality. Then you change the laser scan patterns, and you also use different kinds of lenses to minimize the beam distortion during the scanning. Then you have almost zero oxygen content, like 0.3, 0.4% carbon, and you have completely inert atmosphere inside the build envelope. So in the standard way to make these parts using selective laser melting, uh, you have to have the parts attached to a base plate. So this is done to keep the metal part from uh, distorting due to residual stresses, but it does reduce the design flexibility. So you can't make a completely thick part that is just smack dab on top of the build envelope. So whatever support you have, you need to machine or cut, and then you have to post process it in order to get a good surface finish. So people have come up with new ways to make these materials. For this process, it's based on electron beam melting. Uh, and this process was developed originally at Chalmers University in Sweden, and it was commercialized by Arcam AB. And in this case, it scans across a thin layer of pre-laid powder. It causes localized melting and resolidification as per the slice cross section. So these are some of the differences between E-beam melting and selective laser melting. So in selective laser melting, uh, there is no limitation to the type of powders that can be or materials that can be built. Whereas in the case of electron beam melting, it has to be conductive, so which means it can only use metal powders. So this is a schematic of an EBM apparatus. So what I would like to do is to set up a homework assignment. I don't know if this is homework assignment number 4 or 5. I do not know. It could be 5 because I've been seeing 4 coming through in the last couple of days. So I'm going to change this to homework number 5. And this is um, for you to go in and check out the difference between EBM and selective laser melting process, and describe the difference between the two processes from the perspective of how the beam or laser energy is transferred to the powder particles. And I would also like you to comment whether the process makes a difference between the type of powders that can be applied to the AM process or not. Okay, so that's about it I have for lecture 7, and I will continue in the next lecture later.